Hey guys, welcome back to my channel. So today we're going to be starting a new video series on real analysis. And the reason I decided to start this video series is essentially because it's one of the most challenging subjects in all of graduate mathematics. And it's the first pure math course that most people deal with. So I remember when I learned real analysis, I found it pretty difficult, and I know that was the case with most of my friends as well. So, 4 years after having taken my real analysis course, I think I'm a lot better at it and I'm better placed at explaining the concepts in an intuitive way and not a mechanical manner, like I was taught. So, yeah, let's get started. So, the first question obviously is, what is real analysis? And as the name very clearly suggests, it's to do with the study of real numbers, right? And what about the real numbers? So basically you study about some properties of real numbers, then you learn about theorems and a bunch of other analytical tools that will help you get more clarity on what the real numbers are all about. So the thing is, we've been dealing with real numbers from high school without actually understanding about when their properties are actually valid and when they're not. We've always assumed for granted that things work. And that's the first place most people find an introduction to abstract math a very difficult thing to deal with. So in abstract math, you always have to ask questions. You always need to deal with understanding when something works and when it doesn't. And we'll talk about this a bit later. So what do you learn in real analysis? So in real analysis, you learn firstly about some basic set theory, which is what we'll be dealing with today, which will form the basis of you understanding what the real system is. Apart from sets, you'll learn about topology. So, and topology is going to be the most important topic of real analysis in general. So you'll learn about metric spaces, you'll learn about compact sets, you'll learn about something called connectedness. Sorry for my spelling. And a bunch of other topics like that. Then after topology, you'll deal with sequences essentially, and then series and so on. We'll even deal with integration and all of that. So the thing is that even though we've learned some of these things before, maybe in school we've learned about sequences and series, we've learned about set theory, we've learned some of these things in school before, but we've never ever understood the detailed explanation of how these things work, and real analysis mainly deals with that. So I'm going to talk about what my plan for this whole video series is. The first thing I'd like to point out is this is not a course. Like, this is not a standalone course. That's not the intention with which I'm making this video series. I'm making this video series with the intention of providing some good ideas and intuitive examples on how to understand real analysis and how to study it and how to get a basic or a better understanding of abstract math in general, right? That's what I'm planning to do here. So I'd like to stress that I'm not a PhD in pure math. I'm a math graduate and I have a very good understanding of real analysis, but it's possible that I do make mistakes in this video series. And if you see that I'm making any mistakes, please make sure that you drop a comment immediately or reach out to me. I'll link the ways you can contact me in the description, and I'll make sure that I correct the mistakes immediately. Now again, reiterating, I don't expect people to just watch this lecture series that I'm making and not go to class and expect to do well in real analysis, because that's not the intention with which I'm making this video series. Now that being said, who is this video series for? This video series is going to help math graduates, obviously, those of you who are studying real analysis or those of you who are studying topology and want an understanding of real analysis. It's also going to help physics graduates who deal with a lot of results which are drawn from real analysis, topology, and so on and so forth. It's also going to help people who want to understand what pure math is like. So those of you who are thinking about whether or not to take a pure math course, this might help you figure out whether this is something you want to do or not. And I plan on releasing one video every Monday, and my videos are going to be filled with more examples and ideas rather than proofs. I'm going to be dealing with definitions and understanding definitions, obviously, because I think that's a very important part of real analysis. But with respect to proofs, I may not be dealing with a lot of proofs, but I might be giving you some ideas on how you can prove certain theorems. So, like I was just saying, definitions are extremely important. So why are definitions important? So why is it so important for us to actually learn about definitions? So the thing is, definitions actually give you a lot of insight into concepts, right? They give you a lot of insight about a particular concept. So let's say I'm dealing with set theory. If I have a definition about set theory, in school we were taught that you don't need to really spend time understanding a definition. A definition is just given to you, you learn it, and that's pretty much it, right? But that's not the case with real analysis. In real analysis, when you get a definition, you first have to ask yourself a few questions. And this is what I ask myself. So the first question I ask myself is, what is it about? The second question I ask myself is, when is it valid? Is it valid everywhere, or is it only valid sometimes? And then the next question is, where can I use it and how, right? Because you need to understand how you can use a particular definition. Otherwise, there's no point, really learning it. And always make your own examples and use your own examples to understand what a definition really means. So the last thing I'd say is play around with examples. And in today's lecture, even though it's an introduction, we will be dealing with a few definitions, and I'll show you how to break down a definition and how it actually gives you a lot of insight into the concept you're dealing with, right? So my lecture series or my video series is mainly going to be focused on breaking down definitions, understanding the concepts that are important, and also some examples which will help you remember these concepts better. So without further ado, let's actually get started with some real analysis. And the first thing we're going to be dealing with today is about ordered sets. So as you can see, we are dealing with ordered sets. So obviously when you see ordered sets, the first question that's going to come into your mind is obviously, what is an order, right? So I'm going to take an example to demonstrate this, and then we'll deal with the formal definition in mathematical terms. So let's say I have a set S1, right? And it has a person A, it has a person B, it has a very tiny person C, it has a person D, and a person E. So the set S1 essentially consists of 5 people with distinct heights. So the property that distinguishes the elements in the set is the height, right? So now what I'm going to do is I apply a relation. And for those of you who don't know what a relation is, or if you're confused about it, relation is nothing but a way in which you can compare different entities. So if I wanted to compare a father and a son, the relationship is family, right? A person is another person's father. That's a relationship, right? If someone is shorter than another person, then we are using height as a form of relating to people. So a relation is nothing but a way in which you can compare different entities. So let's say I define a relation in this case as follows. Lesser height comes first. That's the relation I'm defining, that if someone has lesser height, they come first. So what happens when I apply this relation to this set S1 on application? So I apply, sorry about that, I apply to S1. What happens is I get a new set S, right? In which I have to basically arrange the elements such that this relation is satisfied. So the way that can be satisfied is C is the shortest person. So C has to come first. The next shortest person is A. So then A comes, and then B, then D, and then E. So if you can see, what happened is I had a set S1 in which the arrangement of the people or the entities in the set didn't matter. If A was the first element or E was the first element, it wouldn't really matter to me, right? Because at the end of the day, S1 just represents a set of people with distinct heights. But then what I did is I applied a relation. And when I applied this relation to the set S1, what happened is I got a very specific arrangement of elements in the set. Or in other words, I essentially got an order to the set. So what happened is I basically induced an order on this set S1. And the resultant set, which is ordered, is the set S. Now this is just an example. So let's actually deal with the formal definition of what an order is. And then we'll come back to this example and understand it better. So if you see here, the definition of an order is defined as follows. So we assume that S is a set. Then an order on a set S is defined as follows. So if a relation which is denoted by the lesser than symbol has two properties. So I want you guys to understand something here. This lesser than symbol that we use here is just a notation, right? It's just notation. We can use this lesser than symbol to define any relation we want. This lesser than symbol can be used to define a relation which means greater than, right? So this is just notation of a relation. I just want you to understand that and not get confused, because in real analysis, the notations tend to be a bit confusing. Okay, and another thing I'd like to stress here is that this relation, this symbol means two things. So if x less than y, I'm going to call the symbol less than for a few seconds. So if x less than y, we actually term that, or we call that x less than y. That's a valid way of saying it. Another valid way of saying it is x precedes y, or x comes before y, right? That's pretty much it. And I hope you guys understood that. So yeah, so if a relation less than has these two properties, the first property being if there are two elements x and y in the set S, then only one relation can be valid between the two elements. So either x has to be equal to y, that means they're the exact same element, or they're equal. And the other possible relations are x has to precede y, or y has to precede x. So only one of these can be valid, right? That's the first property. The second property is that if I have three elements in a set S and x precedes y and y precedes x, then x precedes z. This is commonly called the transitivity property, and you would have all come across this in some shape or form before. So just to repeat, if these two properties are valid, so if a relation less than has these two properties or satisfies these two properties, then it can be termed as an order. Cool. So let's go back to the example and check if that relation that I defined is actually an order or not. So over here, if you see, the relation is lesser in height comes first. So let's check the first property. The first property says for any two elements in the set. So let's take two elements. So let's take B and C. So the first property says for B and C, only one relation can be valid, that either B has to be less than C, C has to be less than B, or they have to be equal. So very clearly, C is lesser in height than B. So only one of them is valid. So that's great. So what about the second property? So let's take another element D. So we know C is lesser in height than B, and we know B is lesser in height than D. Does this imply that C is lesser than in height than D? The answer is, in fact, yes. The answer is yes, it does. So if you see, C is lesser in height than B is lesser in height than D. So this does necessarily imply that C is lesser in height than D. So both the properties are valid. And in fact, this relation, whatever we defined, is an order. Cool. So now another important thing for us to understand is what is an ordered set. So very simply put, an ordered set is nothing but a set S in which an order is defined. So if we go back again to our example, this set S has an order defined on it, right? It had a relation defined on it. And now we concluded that that relation is in fact nothing but an order. So we can actually conclude that this S is an ordered set. And why is that? Because we know the relation is an order and the relation is defined on this set. So it's in fact an ordered set. I hope this is clear to people, and the reason I'm going extremely slow and using non-mathematical examples in the first few lectures is so that everybody can follow and get an idea of how to think about these things. So let's move forward. So we now know what an order is. We've defined what an ordered set is. So I'd like to mention one thing here, which is of importance to us, and it's about this symbol, the relation symbol. So in fact, from our high school and middle school days, or from when we were kids and learnt about numbers, we've always been taught that this is less than, in the sense that it means that if x is less than y, that implies y minus x is a positive number. So we've been taught from our early days that if x is less than y, that necessarily means that y minus x is a positive number. And this is the relation that's being used, that has been used on Q, which is the set of rationals, the set of real numbers, natural numbers, and everything. So we have always been taught that that's what this means. I just wanted to clear that out so that you guys have some clarity. And like I said, this is just a notation. We can use it to define anything we want, any relation we want. If a relation satisfies these two properties, it's an order. If not, it's just a relation. Cool? Great. So now we're going to go ahead, and the next thing we're going to learn about today is the very, very important concept of what an upper bound is. So I'm going to take an example again, and this time I'm going to take an example of a set S. And let's say it has elements k1, k2, k3, a1, a2, and a3. It's an ordered set, and it's arranged, the elements are arranged in increasing order of height, let's say. So k1, k2, and k3 are three kids, a1, a2, and a3 are three adults. So that's just the way I'm defining this set. So there are three kids and three adults, and the set S is already ordered. That means k1 has the smallest height and a3 has the largest height. We know this. Cool. So now I'm going to take a subset of S. Okay. So I'm going to call that subset E. So let's say E is nothing but just the kids, right? K1, K2, and K3. So let's say E is this subset. So if I ask you to find an upper bound, so if I ask you to find the upper bound of E, what would it be? So you might have a few questions immediately. So does an upper bound of a set necessarily have to belong to it? So does it have to belong to E, or can it belong to S? That's a question you might have. The next question you might have is an upper bound unique? So can there be only one upper bound, or can there be multiple upper bounds? So these are a few questions you might immediately have. So what we're going to do is we're going to look at the formal definition, and we'll come back to this example and solve it. So for now, you might have these questions, but in a few seconds, this will be solved. So the definition of an upper bound is as follows. So let S be an ordered set and E be a subset of S. If there exists a beta in S such that x less than equal to beta for every x in E, we say that E is bounded above and we call beta an upper bound of E. So this might seem like a complicated definition, but let's break that down. So first of all, we have an ordered set S, which is straightforward, and then we are taking a subset of E and we are asking questions about E. Cool. Now we've taken a subset and we're asking questions about that subset. So if there is a beta in S, so this is the first thing to notice, that if there's a beta in S such that for every element in the set E, x is less than equal to beta, then we call beta an upper bound and E is bounded above. So let's go back to that example and apply this definition, and then we'll get a better understanding of it. You might still be confused by this definition, and that's perfectly fine and perfectly normal. That's the whole reason we have examples. Cool. So going by the definition, the upper bound, I'm going to call it beta. According to the definition, it can be in S. Cool. So for the sake of completeness and just so that everybody can understand, and we're going slow in the beginning, let's take every element in S and check if it can be an upper bound or not. So let's take K1. So can K1 be an upper bound of E? The answer is obviously no. And the reason it's no is because K2 and K3 are not less than K1, right? So the reason is, so if I were to write the reason, K2 not less than K3 and K1, and K3 not less than equal to K1. So K1 can't possibly be an upper bound. And for similar reasons, K2 can't be an upper bound as well, because K3 is not less than equal to K2. So very obviously, K3 can, in fact, I won't write can here because is an upper bound. And why is K3 an upper bound? Because we can see that K1 less than equal to K2, K2 less than equal to K3, K3 less than equal to K3. So cool. So K3 is an upper bound of E. I hope that's clear to everybody. Now comes the question, is K3 the only upper bound of E? Are there any other upper bounds of E? So the answer is simply that A1, A2, A3 are also upper bounds of E. The reason is we just saw that an upper bound can be in S. So A1, A2 and A3 are in S and it satisfies this property. So K1 is less than equal to A1, K2 is less than equal to A1, K3 is less than equal to A1. So A1, A2 and A3 are also upper bounds of E. So some of your questions have clearly been answered and I'll summarize them. So what you need to understand about an upper bound is that it need not belong to the set E, it can come from the set S, right? That's the first thing to take away from this. The second thing to take away from this is that an upper bound is not unique in the sense that there can be multiple upper bounds to a particular set. Now comes a very important thing, right? After this, now that we've understood what an upper bound is, and I'm just going to erase this so that it's clear and you guys can read it. Okay, so now we move on to the least upper bound or the supremum, which is something that all of you would have heard of before. So we're talking about, sorry about that, we're talking about the least upper bound. So let S be an ordered set, E be a subset of S, and E is bounded above. So these are the premises under which we are talking about this particular definition. So if these things are valid, then we can talk about this particular definition. So for E to be bounded above, that means it has to have at least one upper bound, right? I was just clarifying that. So now anyway, suppose there exists an alpha in S with the following properties. 1, alpha is an upper bound of E, and 2, for gamma less than alpha, if gamma less than alpha, then gamma is not an upper bound of E. If these two are satisfied, then alpha is a supremum, is the supremum in fact of E. So what does this mean? So let's go back to our example and try to understand it. So just bear with me for a second and we'll get through it. So here all the upper bounds are in fact, if I were to write this properly, K3, K1. So K3, K1, A1, K3, A1, A2 and A3 are all upper bounds of E. Right. So now if I am to talk about the supremum of E, what essentially the definition says is, if alpha is an upper bound of E. So for it to be a supremum, first condition is it has to be an upper bound. So let's look at the upper bounds, K3. So K3 is an upper bound. And now if any element is less than K3 in the set E, then that element can't be an upper bound. That's what it says. So K2 is less than K3 and K2 is not an upper bound. That's correct. So K3 is the supremum of E. Now, is K3 the only supremum? Can there be two supremums? Is that possible? Let's think about it, right? So can A1 be a supremum? Think about it. So if A1, let's say A1 is a supremum, A1 is upper bound, so that's satisfied. But what element is less than A1? K3 is less than A1. And is K3 an upper bound of E? Yes, it is. So it violates the second property of the definition. Therefore, A1 can't be an upper bound, can't be a supremum, A2 can't be the supremum, and A3 also can't be the supremum. Therefore, K3 can and is the only supremum of E. I just wanted to make that amply clear, and that's why I went over it again and again. So, to be clear again, we have dealt with upper bound and we've dealt with supremum. And now we're going to deal with one last quick concept, and that will be the end of this lecture. So this concept is in fact called the least upper bound property. So it's defined as follows. An ordered set S is said to have the least upper bound property if the following is true. So if E is a subset of S, E is not empty and E is bounded above, then the supremum of E exists in S. So again, if we were to go back to our example, E is a subset of S, E is not empty, E is a subset of S, we know that E is not empty because it has elements K1, K2 and K3, and we also know that E is bounded above because we know the upper bounds of E are K3, A1, A2 and A3. Now what is the supremum of E? The supremum of E is K3. We literally just discussed about it. So the supremum of E, which is K3, in fact lies in S. K3 belongs to E, which is a subset of S. So K3 belongs to S. And therefore this set E in fact has the least upper bound property. Now I'm going to leave you with one question, and you can think about it, and that'll be the first thing I discuss in the next lecture. So does Q follow the LUB property? Q being the set of rationals. And if yes, prove it. If no, give me a counter example. So this is a question for you guys to just think about till the next lecture. And this will be the first thing I discuss in the next lecture. So I hope you guys enjoyed this. And if you have any comments or any feedback, make sure you drop a comment and I'll get to it. So thank you so much for watching, and I'll see you in the next video.